I don't know for the participants whether it's good evening or good morning. For Fernando, our speaker, our guest is good morning. For the rest, mostly I guess good evening, or good morning. Let us start this evening, this after work, which is a short course on the topic of rediscover the basics of machine learning. Today, 17th January 2025. Up. In the framework of EAGE, European Association of Geoscientists and Engineers, which is founded in 1951, we are having this after work. It's a professional non-profit association for geoscientists and engineers, and the main goals are to promote the development, innovation, and application of geosciences and related engineering subjects, and also to foster the communication, fellowship, and cooperation between those working and studying or otherwise interested in the geosciences. EAGE Annual Conference and Exhibition is the biggest and the most important event that EAGE has. It's an annual event on June each year. This year, it will be at Toulouse in France, with more than 6,000 participants, more than 1,300 presentations, and over 200 exhibitors. I invite you to verify the website if you are interested in this big event. But the very next event of EAGE is the 5th EAGE Digitalization Conference and Exhibition, which will be in UK, Edinburgh, enhancing predictions and investments with digital technologies. EAGE have several local chapters. This event is going to be held by Paris Local Chapter. In France, in addition to Paris, we have another local chapter at Toulouse, and also, at Pau. And there are some other local chapters in Europe, and also you can see that in Azerbaijan also there is another local chapter who are our guests for this evening, and I will ask them to present the local chapter of the Paris after this presentation. The local chapters have the goal, have the objective of linking the. Pardon?
Yeah.
Is there any question? The local chapters have the objective of linking the local experts in the geosciences and to have the smaller events like this one that we have together with a smaller audience. Let us introduce you to local chapter of Paris with the president Laura Mosga, vice president Emilio, and Guillaume, me, and the other team member you can see. It's a multinationality, also multidisciplinary organization. If you'd like to join us to give a hand in a friendly environment, I invite you to contact us. You can find us on LinkedIn or simply send us an email. Here is the email of the local chapter to meet people and also to help in organizing the events like this one. Last year, 2024, we had the privilege of being selected as the best local chapter of 2024. During the annual meeting of EAGE at Oslo, the award was given to Paris local chapter that last year. I want to invite Leila. If you hear me, Leila, I can share. I can continue on your slides in order to introduce Azerbaijan local chapter. So
Hi, everyone. Can you hear me?
Yes, we hear you. Perfect. And let me only change the presentation to yours. So Here's yours. Share it.
Okay.
Yes, please, Leila. I'm ready.
Good evening. It's evening in Baku now. Let me shortly introduce myself. I am Leila Alimuradova, Executive Secretary of EAGE Local Chapter Azerbaijan. I work for SOCAR, State Oil Company of Azerbaijan, in strategic development segment. And at the same time, I'm lecturer on petrophysicist, well logging, and reservoir evaluation and management in several high schools of Azerbaijan. Now let me continue with my presentation on local chapter Azerbaijan. First of all, I would like to thank Guillaume as well as Pedram, Mr. Pedram. I hope I pronunciate your name correctly.
Perfect, thank you.
And I would like to thank local chapter Paris for this opportunity. I truly appreciate it. Thank you so much. And straight away, I will begin by providing an overview of our local chapter's foundation, highlighting a current activity of our society, and outlining our plans for 2025. EAGE Local Chapter Azerbaijan was founded in October 2002, and the leader of our local chapter was, and now also our president is Dr. Akif Narimanov. I joined EAGE in 2009 as executive secretary of local chapter and have been serving in this role ever since. On the next slide, that is the slide about turning point of our activity. It came in January 2010 when we signed the collaboration agreement with societies which was active in Azerbaijan. That is Azerbaijan Society of Petroleum Geologists and National Committee of Geophysicists of Azerbaijan. And on the picture, that is the picture of that from that moment. In the middle of this picture, our president. Now on the next slide, let me highlight some key points of our activity. We have organized 10 international conferences in partnership with such societies as EAGE, EAPG, and SPE. Then together with ESPG, we held 15 Republican conferences dedicated to outstanding Azerbaijani scientists, such as Shifayet Mehdiyev and Akif Alizadeh. And since 1996, we held 28 international student conferences. Usually it happens in April of every year. In addition, we organize scientific workshops, seminars, field trips. Some photos from field trips you can see on the next slide. That is the picture from different field trips. Even we organize field trips for the specialists of foreign companies which are operating in Azerbaijan. In the next part of our presentation, I will tell you about our activity of today. So today, you can move, yes. Today, we continue our activity with around 50 members, including 25 student members. And looking back at our activity in 2022, which are indicative of trends of other years. These slides are from our report to EAGE. So mostly we organize the same type of events. That is 3 major events with about 100 participants. And on the next slide, you can see the pictures from events. That, for example, here we shown pictures from International Conference of Students. When it comes to student engagement, the information given on the next slide, the following student chapters established with our support. First one was in 2010. The second one was in the 2018. That was established in UFAZ. We have university, as French Azerbaijan University we have in Baku. And most recently in 2023, the student chapter was founded at Khazar University. The next slide, please. About best local chapter. So our efforts have not gone unnoticed. So twice in 2014 and in 2018, our society was recognized as a EAGE best local chapter. And I came to the last part of my presentation, the next steps. Looking ahead, our plans for 2025 are ambitious, and some of them are outlined on this slide. At the end of January, we are planning to organize short training course on petrophysics for students from Khazar University student chapter. In April, we will hold our traditional student conference. Then we are planning during the summer of this year, we plan to attend EAGE annual conference in Toulouse and look forward to meeting with you personally there. And of course, we are willing to collaborate with other EAGE student chapters on joint events. So that's all the information I wanted to share with you. And thank you very much for your attention.
Thank you very much, Leila, for this nice presentation. And you have some annex to here.
Yes, that was additional.
By the way, thank you very much. Very complete presentation of Azerbaijan local chapter. If the participants have any question regarding the local chapters, you can contact them directly. I think that you can find them easily on the website or on the LinkedIn or simply sending an email or message to them. So let us continue with the next events that we will have. Today we will have Fernando for this training, but after this event, which is for today, we will have in February another event about distributed acoustic sensors from design to data recording and processing. It will be a hybrid event. It means you can join us either online, or if you are in Paris region, you can join us at Clamart, Chalon-Berger. The speakers will be from Chalon-Berger, Joël Calvet, and also the Stan Nziengui from Phoebus Optic. Today, after the presentations that me and Leila did for you, we will have a lecture of Fernando Vizeu from Aspen Technology. It's a short course, in fact, so with a brief introduction to computer vision and convolutional neural network, and also preparing the F3 seismic dataset, obtaining and loading the data and building an input pipeline. The third part would be semantic segmentation using PyTorch. The fourth will be evaluating and improving the results. And finally, future directions, a glimpse into other applications and current trends. If you have any questions, please keep them for at the end. At the end, you can either ask your questions orally or you can write in the conversation part. So I will ask the question from Fernando. But who is Fernando? Fernando Vizeu, bachelor and master degree in petroleum engineering from Universidade Estadual do Norte Fluminense. Excuse me for my accent, for my bad accent. From Brazil, started his career as software developer at Paradigm. Currently, he is senior data scientist at Aspen Tech, as I explained, in the office of Montreal. He develops artificial intelligence applications for geosciences. So, Fernando, please, if you want to share your screen, you're free. Share your screen and go up with continue with the presentation. Thank you very much and have a nice evening.
Can you see the screen and can you hear me?
Perfect.
Okay. First of all, thank you for the Paris local chapter for inviting me and for everyone that came here to this short course. So I was already introduced, so there's no need for me to introduce myself again. And in this presentation, as Pedro said, I'll cover a little bit, like very quickly, a few topics related to computer vision applied to geosciences. This material that I prepare here, there is a source code in Python that is available, like in this slide, I have the link for it if you want later to go through it. But because of time constraints, I will not go into the code. I'll just show the main results, but you feel free to explore it later. And so for this reason, I will not go into details like of the input pipelines and so on, because otherwise we would lose too much time in the code. And maybe not everybody's interested in the coding part, so that's it. Another note is that I sent to the organization, for some reason, I sent PyTorch, but actually the code uses TensorFlow. So this is also a little difference. So sorry for that. And okay, let's go to it. So first of all, I like to start to explain like this AI landscape, because there's a lot of terminology related to AI, and sometimes there's a lot of confusion between, for example, what's AI, what's machine learning, what's neural networks. So I like to make it clear to start. So AI, I consider as the large field of computer science that is trying to create intelligent agents to perform tasks. So these agents can be deterministically programmed, like deterministic rules set up by the person that's creating them, or they can be using machine learning. That's a subset of AI, where these agents, they learn from the data. So usually when we talk AI, we are mostly talking about machine learning nowadays. And also there are a few like specific areas inside. For example, neural networks. That's a category of algorithms in machine learning that they were initially inspired by the human brain to mimic the behavior of the human brain. And so this is a type of machine learning algorithm. So it's not like a synonym for AI. It's just a subset, let's say. And so, as I said, the neural networks, they started as trying to mimic the behavior of the human brain. So they are composed of neurons. So this here would be a neuron, and it gets the inputs from previous neurons, for example. It processes it somehow, and it outputs what it was processed to other neurons. And when these neurons, they are organized like this in layers, and each layer receives the output from the previous layers and sends then outputs to the next layer. This is what's called a neural network. So you can see like this animation that the data is being transformed in a vector and is fed forward through this network. So layer by layer, the information passes until in the last layer, the network makes a decision in this example to classify this digit into what this digit corresponds to. So this is like very quickly what neural network is and how the neural network learns. So they learn using algorithm called backpropagation, where we start with like these parameters of the neural network are randomly initialized, so we don't know anything about them, and we feed them the data that we have, the knowledge of what we're expecting from that data. We feed it through the network. The network at the beginning will produce garbage, but we use this algorithm called backpropagation to try to tune the network parameters to better fit what was expected, what we know was the expectation that what the network would produce. So again, like very quickly going over it. And convolutional neural networks, they work by replacing that image that I showed before of the neuron with a convolution operation. So a convolution, in simple terms, you can think of it as like a moving filter going through an image. So in this example here, in blue, like in the bottom here, I have the input image, and there is what's called the kernel of the convolution. That's this like gray thing here that's moving. It slides over the image, and at each position, it will produce a new result that's in this top image here in green. So the convolutional neural networks replace the traditional neurons with convolutions. And these convolutions, their input is an image, and the output will also be an image. So as you can imagine, to deal with images, the convolutional neural networks are much better in general than traditional fully connected neural networks, because they have these properties intrinsic to images that the transformation is considering the neighboring pixels, for example, and so on. In this example here, I show like how it works in this website here, CNN Explainer. You can go on it and try it for yourself. But you see here that this image of a mug, for example, it had like 3 input images that were the red, blue, and green inputs. And each of them is being convolved with a kernel that's moving here and is producing an output. And then these outputs will be combined to the next layer, and will be used again, will be convolved with new set of kernels and produce a new sets of output, exactly like I showed in the simple neural network, but now with these convolution operators. And you can produce like a convolutional neural network with tens of layers, maybe sometimes hundreds of layers, that at each step you see it's generating new images. So the convolutions you can think of as filters. So it's filtering the previous inputs, producing new images, sending them to the next layer that's doing the same, but now on these intermediate inputs, and so on. And in the end, you get like high-level features that can be used in this case to categorize what this image is of. So in this case, this network predicted that this image is an espresso, and there's other categories that it didn't predict, so it predicted correctly. And again, you can explore this website. It's a really cool website that you can look inside how these networks work. And finally, computer vision. So computer vision, I had like my first slide, is a subset of AI as well. And it's the subset that's regarding everything related to finding objects or patterns in images. So it can be detecting faces, for example, in your cell phone. When you try to unlock your cell phone with your face, it's using computer vision. That are traditional computer vision approaches that are not necessarily called machine learning. These are, let's say, the traditional computer vision that you find in libraries like OpenCV. And now there's computer vision using machine learning. It was mostly started with neural networks, and now convolutional neural networks, and nowadays vision transformers and so on. So they are using these machine learning techniques to learn how to do this computer vision tasks on images, but learning from the data. So you provide to this network the input image and what you want it to predict, and it will learn to do this prediction for you based on the data. And a few tasks that we have in computer vision, for example, the first one here is classification, where for an image, I just give a label. For example, this is an image of a cat. There's also semantic segmentation, where you are interested in, for each pixel of the image, to obtain a class. So for example, here in this image, it had 4 classes: grass, the cat, the trees in the background, and the sky. So for each pixel, it will try to predict one class. There's also object detection, where you want to create bounding boxes around the objects that you want and label them as well, like say what object is which, and so on. So instance segmentation. In this example here that I'll show you in a few moments, we are interested in doing semantic segmentation. As I said, at labeling each pixel of the image as one of the classes of interest. So this is what we will deal with today. So starting with the data set that we are going to use in this example, we are using the F3 seismic data set. That is a data set that's from the North Sea, I think it's in Netherlands, and it was made available by DGB Earth Sciences, so you can download it and you can use, I think, for anything. This data set originally only had the seismic data and I believe the well logs and these labels that we need to train our neural network. They were created by this group here, like they published it in the interpretation journal in 2019, the labels for this data set. So for each, in this case now it's a voxel, for each voxel of this data set, there is now a label that's associated to. In this case, these labels, they are seismic phases. And as I said here, I have as well, we can obtain the data set from the source code as well that I published in this platform, Kaggle. So I think you have these slides later. I don't know, I have to talk with Pedro, but if you can just click here and you will be able to see everything that I'm showing here, but in form of code, if you are interested in diving into the code. And this Kaggle platform is a free platform that has a Python development environment already installed with free access to GPUs, to graphic cards. So it's very convenient to use. But as I said in the beginning, I will not go into the code in this short course because of the time constraints. It would take, I think, a few hours to go into detail into the code. So, but you have access to the code, and if you have any questions, you can send me an email or to ask about it. So we are doing semantic segmentation on seismic data. What this means is that we are, for each pixel of the seismic data, giving a class to it, or each voxel it would be the correct term for dealing with seismic data. So for example, here in this data set that we are using, it has 6 classes. So each class has like its own geological meaning. I'm not a geologist, so I won't go into the geological meaning of each of these classes, but you can visually see that they have like different textures, different geometries, and so on. And we want to train a convolutional neural network to do this for us, to do this classification for us. So the first thing, we need to create our data set. And we have like the data set that somebody interpreted a few sections, a few inlines and a few cross lines for us. And we want to, first thing is to split this data set in train and validation data set. The train data set is what we will use to optimize the network parameters. And the validation data set is what we will use in a blind test for the network to evaluate its performance. We cannot evaluate the true performance of the network in the training data set because it's been trained on it, so it's biased towards it. So we have this blind data, that's the validation data set, to do this evaluation. And in this case, we are using in total 15 inlines and cross lines of this data set, so it's less than 2% of the data. This is what we will train the network. So in a real scenario, an interpreter would do this, like would go to the seismic data and label it somehow manually or using whatever tool they have. And then we would use it in our neural network. Another thing that's important when you are dealing with classification or segmentation is to know the class balance that you in your data set. So in this case, we have a very high imbalance, as you was able to see in this picture here. We have much more light blue faces than the other faces. So the red faces, we have very little. And this can be problematic. We'll see later how to do with it. But it's important to know that in advance, because if you have some problems, you already know that this might be the cause. So it's important in the beginning to look at all this information about your data set. In some cases, we need to do pre-processing in the data. For example, some algorithms, they require the data values to be within a range. For example, some algorithms require them to be between 0 and 1, like the values, or between -1 and 1, or with mean 0 and standard deviation 1, and so on. So you have to pre-process the data to fit these requirements from the algorithm. So for example, the input here that we are using is the seismic amplitude, and the values of seismic amplitude can vary, have a wide range of values. So in this case, the data was already normalized to have mean 0 and standard deviation 1. So we didn't need to do this pre-processing step, but it's good to keep in mind that it can bring problems later. And another thing that you might have to do, that we did in this case, is to split our data into smaller parts, because this seismic section, it was like 900 traces by about 500 samples and the depth. So it might be too big to fit into memory, especially because most of these AI methods, they run on GPU, and the GPU memory is usually more constrained. So sometimes we need to do this, is to do random cropping of the data in smaller pieces so that it can fit into memory. So there are a variety of pre-processing tasks that might be needed. In our case, we only needed to do this cropping in smaller pieces. So this it was the input pipeline for the data. We needed to load the data, to split the data into pieces, and now the data is already ready to train in our TensorFlow model. So first, we need to select the model that we are going to use. And if you study a little bit of semantic segmentation or image classification and so on, you know that are a variety of models in the literature. So I would recommend you pick one of those models. There's also a variety of models already implemented. For example, in TensorFlow, there's already a library of semantic segmentation models implemented that you can use. In PyTorch, the same thing. And in this case, I selected this model that's called the All-Air ASPP. That's a semantic segmentation model that's very lightweight. So it's very quick to run for the purpose of running in the lesson. So it would run really quickly, but you can swap this for a more robust model or whatever. And this is the architecture of the model. So it has a MobileNet v3 backbone. So this is like a very famous convolutional neural network that was is published here in this paper here with this link. And it adds a few convolutional layers. So you see this conv2D are convolutional layers that I explained before, and a few other things on top of this MobileNet v3 backbone. And this can be used, is a convolutional neural network that was developed for semantic segmentation. But you, as I said, you can choose a different model than that. In the code that is available, it's using this specific model. Then with the neural network, you define a few more parameters. For example, the optimizer. That's the part of your workflow that will do that back propagation process that I explained in the beginning. It's called the optimizer. In this case, we are using one that's called ADA, that's available in TensorFlow, so we don't need to do anything. We just specify that we are using this. There are other types of optimizers. ADA is one of the most used ones. You need to specify things like the loss function. That's how the optimizer will compare the result that your network created from the result that's expected. So this is called the loss function. The batch size is how many examples you will fit into the model at once. The number of epochs is the number of times that the training loop will go through your data set. So all these parameters you defined before you start training, they are like hyperparameters, let's say. And once you have defined them, once you have the data, and once you have the model, it's really simple to start training. You just send a TensorFlow command, and it will start training. In this case here, if you run in the code in Kaggle using GPU, it takes like about 5 minutes in this setting that I provided. And after that, you will be able to see, for example, this graph here. So this graph is like the evolution of the neural network with respect to the epochs. So the epochs is each iteration that the network went through the data set. So you see here, for example, in orange is the loss function that's decreasing. So the objective of the optimizer is to decrease the loss function. And other metrics, for example, the accuracy of our network is increasing with the training. And the intersection over union, that's another metric, is also increasing. So that's good. And that's good that the loss is decreasing as well. So we see that our training is, in summary, is converging. But if we zoom in, we can see that it has some problems. So the first problem that we can diagnose right from this graph without looking into the data, into the results at all, just analyzing this loss graph of the neural network, is we can diagnose what's called overfitting. So overfitting happens when during the training, the optimizer is doing its job, is reducing the loss value as the epochs go on. But at some point, the validation loss, that's what I mentioned in the previous slides, is what's calculated in that blind data set that was set apart. So this validation data set's not using training, so it's a blind test. And after each epoch, we predict the results in this validation data set, and we calculate, in this case, what's called the validation loss. So there's this graph here, and we see that's not as low as the training loss, for example. So this is expected. It's fitting to the training data set, not to the validation data set. So it's expected to be the validation loss to be higher than the training loss. But what's not good is the validation loss increases after some time. This is what happened here. This is one of the diagnoses of overfitting. That means that the neural network, after some time, is learning how to mimic the training data set, and is not being able to generalize as well to the validation data set, to the blind test. So it's performing really well to the data that's seen in training, but not to new data. It's like if you study to a test and your professor gives you 100 questions and you ace all these 100 questions, but in the test, he gives you 5 new questions and you do terrible in these 5 new questions. This is more or less the same problem here. It's you're overfitting to the training data set. And we don't want that, because when we apply the network, we're applying data that never saw before. So it's when we apply the network, it's more similar to the validation data set than to the training data set. So we will see in a few slides how to overcome this. And of course, we can look at the results that we produced. So here I'm showing the validation data set. the 3 sections that were set apart, and what our network predicted. So you can see that it did a pretty good job in most of the data, especially like these blue faces. It didn't do so good job in the like hot color face, like the yellow, the orange, and the red. So we will analyze why in a few moments, but this is already one way that you can evaluate your model, just looking at it, looking at the results. So now we'll see other techniques that we can use to evaluate the results and also to try to improve them. So the first thing that's really commonly used is the confusion matrix. So the confusion matrix, what we do, I'll go back a little bit, for each position here in these images, in these sections, we record what was the true label. In this case here, where my mouse is the dark blue, and what was predicted. It was predicted dark blue. Okay. In this position here, what was the true label was orange, but what was predicted was light blue. So we record this for all points in your data set, all voxels in the predicted data. You record it and you build this matrix. So this is exactly what it's saying. So for all the voxels, 113,000, they were dark blue, and they were predicted as dark blue. But 1.8 thousand, they were dark blue, but they were predicted as this other blue here. Another example, of those that were predicted as red, as these red faces, 3.6 thousand, they were actually the orange faces. So you can look at this table and you can gather a lot of information of how your model is performing in a class, in a faces by faces basis. So this is really interesting. But since this is in absolute values, it's hard to see, it's hard to interpret, because we saw that, for example, this light blue class, it had much more data than the others. So it's natural to expect that it will have much more correct points than the others. So to interpret it, we normally normalize the confusion matrix either by column. So in this case here in the middle, it's normalized by column, meaning that all the columns sum to 100%, or normalized by row. In this case here, all the rows, they sum to 100%. And how do you read that? So for example, in this green square here, we saw that from all the pixels that were classified as this orange class, 7% of them, they were actually from the yellow class. So the network is mistaking when it says it's orange, 7% of the time it was actually yellow. So in this case here, it's even worse. When saying it's red, actually 27% it was orange. So if you look at the one that's normalized by column, if you look at the one that's normalized by row, you read it like in a similar way, but looking at the actual classes. So in this case, from the samples that were actually this middle blue here, 90% were classified as middle blue, 7% were classified as light blue, and so on. So here you can have more information of how your model is performing when you normalize the confusion matrix. But we can synthesize even more, like compress even more the information here by using what's called the classification metrics. So probably you already heard these names on these metrics, like accuracy, precision, recall, and so on. These metrics, they are calculated using the confusion matrix. So they use here the TP is true positives, the TN true negatives, FP false positives, and FN false negatives from the confusion matrix, and then they calculate these values here that you can more easily interpret than looking at the table. So what these true positives, true negatives, false positives, and false negatives mean? Like true positives, they are the values that were correct. So the diagonal is the true positives. The true negatives were the values that were correctly classified as not belonging to that class. So they are these like orange elements here. The false positives are the elements that were classified as one class but were actually from the other. And the false negatives is the other way around. It is the column here. So with this from the confusion matrix, you can create this table. So this table is much easier to read. From the same data that we had before, we had those images, we synthesized them into the confusion matrix, and now into this table. So you can see by class, for example, this class here, the Zextin, it had a precision of 61.15%. This means that when it said it was read only 16.15% of the time. And the recall is that from all samples that were read, 91% they were classified as read. So this precision recall are the two main metrics that we usually see in papers and so on. But there's also accuracy, F1 score, intersection over union. You can see back in the formulas that were in the previous slide. But this is, looking at this, we can already see that we have some classes, they are underperforming, the yellow, orange, and red. Some classes are performing well, these other ones. And we see that this correlates to the classes being less frequent or more frequent. So this is the problem of class imbalance that I mentioned before. And so we evaluated these results using our confusion matrix, and this matrix derived from the confusion matrix, and what we can do now to improve the results. So the first thing, that's a really simple thing that you can do, is that we saw that the network overfitted, which means that the validation loss started to increase after some epochs. One simple thing that you can do to avoid this is just stop the training when it starts to happen. So this is called early stopping. And you usually set a parameter that's called patience, is that how long will the TensorFlow or PyTorch, a training loop will wait for how long until it stops the training if the validation loss does not improve. So if the validation loss does not improve for 5 epochs, for example, it will stop the training and get the model that was like the best one that was trained before. So you see that previously I have set it for 100 epochs, and in this case here it stopped at 50 epochs because it detected that after that the model was not improving the validation loss anymore. So it also makes the training faster because you don't need to wait for 100 epochs anymore. You can stop earlier. So this is the first thing that we can do. Other things that we can do is data augmentation. So data augmentation is a technique that's widely used, especially when you consider that your data set is not big enough, your training data set is not big enough, or it has not enough variability, and your model starts to overfit on it. So what you can do is use data augmentation. That data augmentation is basically any technique that you use to increase artificially the size of your data set. Increase the size of your data set without needing more data, more like true label data. So in our case, without need to interpret more sections. So here the interpreter would not need to add more interpretation, like to interpret 10 more lines or 10 more cross lines would be another alternative. But with data augmentation, we do this artificially. So the examples that in the code that I'll provide, we used random noise, so adding random perturbations to the seismic amplitude. So we just add like a white noise to it, and it improves the results. And also to randomly flipping the data. So flipping like horizontally, so that basically mirroring the data. It's important to highlight here that in other applications, we see people flipping the data vertically as well. Usually, we don't want that with these types of applications, seismic, because we have a clear like geological order that our model needs to respect. So we saw in our example that we have like the dark blue faces at the top and the red faces at the bottom. If we flip it vertically, the network will learn to predict red at the top and blue at the bottom. So we usually don't want to do that for some seismic applications, but to flip horizontally usually is okay. So it's a very simple thing that can be done. And finally, the class imbalance. There are two main ways to deal with the class imbalance that we saw that in, for example, the light blue class, it had 50% of the data, and the red class, it had like less than 5% of the data. So there are two things that you can do. One is to increase the penalty in the optimization process for the underrepresented classes. So you can say that add a multiplier to the penalty of the red class, for example. We saw that the red class was doing really bad. We can add a multiplier to the loss. So if the network makes a mistake in the red class, it will be penalized twice as much or whatever number that you decide. So this is one strategy. The other strategy is to oversample the underrepresented class. Is to like, instead of picking like naturally sampling the data, you focus to sample more in the undersampled classes. So in this example that I'm giving, the red, the orange, and the yellow. So you add more samples from that part. So the network will learn more of that part. So after doing all this that I mentioned, stopping the network before it overfits, adding random noise to the input, and flipping horizontally the data, and also sampling more the orange and the yellow and the red classes. After these modifications, running the training again, we obtain the results on the right. So the left is the true label. The middle was the first result that we got when we saw a few slides ago. And the right is the final result after these improvements that we did. So looking like subjectively here, these images, maybe we cannot see exactly what happened. We can notice that it's better. But again, to quantify this feeling that we know that it was better, we can use the confusion matrix and the metrics that we talked about. So in this example, we have like the initial result that we had before, and the bottom here, the final result after the improvements. So like if we focus here, for example, the precision of the red class, it went from 61% to 73%. The orange class, that was not really good. The recall went from 77% to 85%. So you see that in general, we got improvement especially in the underrepresented classes. And if we see the general performance of the network, that is this last row here, we see that our values are better. So that was basically it for this really quick tutorial on computer vision on seismic facies classification. So I know that it was fast, but the idea is to show you the techniques, and then if you are interested, you can explore it later in the links that I provided in the presentation or in the code that I provided as well. And the last slide, I want to talk a little bit about future directions, that we are seeing this AI revolution happening in our lives with ChatGPT, with Midjourney, and with like this plethora of AI applications we see in our daily lives. I want to highlight a few cool applications that I saw from it on the EAGE annual exhibition this year that was in Oslo. So I participated in the conference and I watched a few presentations, and I'm bringing here a few examples of what we can see in the future for seismic applications. So the first one is the diffusion models. The diffusion models, they are the models that are behind these image generation tools that we have, for example, DALL-E and Midjourney. They use diffusion models. And the idea is that you give a prompt and it generates an image for you. So how this can be applied to the geosciences? So one application that I saw in the conference, a few papers actually were mentioned, a few talks were talking about this, is to generate velocity models. So in this case here, this first presentation, you would give as input like the top of the model, like the first layer, let's say the first, I don't know, 10 samples of the velocity model, and what type of velocity model that you want. This would be equivalent to the prompt. So for example, I could ask for a flat velocity model, or for a curved velocity model, or for a faulted velocity model, and so on. So you would give these two inputs, and then this diffusion model would generate like new velocity models for you. So this was an application. And how it works, as I said, is a diffusion model. This diffusion model, it learns by getting an original image, contaminating it with noise, and then training the network to clean the image back to the original image with the option of adding some conditioning. So in the example I showed before, the conditioning was the type of model that you want and that first layer. So other applications of this that I saw there at the EAGE annual conference was this one, that it was conditioned by the type of model as well, if it's curved, if it's faulty, or if it's flat, and a well, like a pseudo well. In this case here, you see that maybe it's hard to see that the velocity of the well here is the same as the velocity of the well here. So maybe it's not easy to see, but you see that what was predicted, that the velocity model that was generated, that's this, let's say, green line, it respects the input well. So you can generate these velocity models respecting conditioned to a well. For example, you have the information of the well logs in your field, so you can generate now this model conditioned to them using diffusion models. This other one was really cool as well, that they also used well logs. So they used two well logs, one in the left and one in this position here. And they conditioned the construction of the velocity model with a text prompt. So the user could write, I want these two wells, a velocity that has these two wells, and has a salt dome intrusion with potential hydrocarbon traps. So it would generate this model here. And depending on the prompt that you give, you see that the wells, they were the same. So the velocity intercalation is the same, but depending on the text that you gave it, it would generate a different model. The other application that I think everybody sees every day now is the chat assistants. So one application that I saw in the conference last year was to use to train a chat assistant to do seismic processing. So in this case, they trained this assistant with seismic Unix commands. So the user would have literally like a chat interface, and you ask the bot, apply a high cut filter with this parameterization. And then the assistant would run the seismic Unix command. So you can see here the command here to your data, and then you would provide your data. So everybody that already had to use seismic Unix, usually in university, know that they have a bunch of commands and it's impossible to keep track of all of them, all the parameters and so on. So they trained the chatbot to do this. So this is like only an example of what it can do. And then trained it with this data set that were the user prompts and what command and the command parameters that the seismic Unix, like the seismic Unix command. So like this prompt should produce this command here. This prompt should produce this command. So they prepared data set with a bunch of these examples and then trained the chatbot to do this and got that result that I showed you before. So this is also, I thought was really cool. And just a reminder, maybe we're not really impressed by it now, but reminding that how these things, they are moving fast. each day moving faster and faster. So in 2023 March, we had this was the video generation model, the state of the art at the time. And less than 1 year later, so it will be 1 year next month, OpenAI released this new model, that's the SOTA. So it moved really quick. So we can expect like these two applications that I showed before, the velocity model building using diffusion and the chat assistant to perform diverse tasks. They are in their infancy, but they for sure will improve a lot in the next year. So keep an eye on that. And I believe that was it for my presentation. So thank you again, everybody, for watching. And if you have any questions, I'm happy to answer them.
Interesting topic and very interesting and important applications. Thank you very much, Fernando, for this presentation. I appreciate. So I come back to the slides. Let's wait for the questions. I have the questions also, but let us first give the chance to the participants to ask their questions. I think there's one question that I saw someone has written here. So feel free to write the questions in the conversation part, or if you want to ask orally, it's possible to open your microphone and ask your question. You can also there's a hand option to ask for the permission to ask your question. Yes, there is a question. First of all, one question is about can you please share the GitHub link later? And I think that the links that you have, they are all in your presentation. Or if you want to share some of
I can put here in the chat if you want. It's okay. But if you want, I can share the whole presentation as well that has the links. So the code link, I think it's here.
Perfect.
And but in the presentation, there's links for a bunch of papers and a bunch of tools, like the tools as well. So let's just check if it's open. I don't remember if it's public. I think it is. If you can open and you can see the code, let me know, because I'm logged in. I can open.
I'm testing.
Okay, so yes. It looks like it works. Yes. So
Perfect.
there you have also some explanation of the code as well, and all these images that I showed are there. So you can just run it if you want. And there's also, this was from a previous course that I taught that was a long-term course. In the end of the slides, there is some challenges if you want to do them. So you can feel free to explore it, and the data set is also included there already, so it's already built in. You can just start running and it should work. So I see there's a question regarding, I'm looking at the chat. There's a question regarding DB scan. Can I answer it?
Please. So for facial segmentation, do you use DB scan for clustering? Please.
So in this case, the example that I showed, I'm using convolutional neural networks. The main difference of what you suggested here, the DB scan, is that the DB scan, at least from my knowledge, is an unsupervised method. So that's why it's called clustering. When you do unsupervised classification, is usually called clustering. It means that it works without the need for the labels. But since it's not labeled, like the data does not need to be labeled, it just like learns the geometric distribution and similarities of the data itself. So for this example that we want to train a network with our labels and then teach it to predict the same thing for us, I don't think it would be appropriate, this DB scan, but other applications, it can be used. Like when it's unsupervised, the DB scan can be used.
Here's another question, Fernando. Thank you for this answer. The other question is from Christian. Have you ever tried using multiple seismic volumes with different offset stacks for classifying?
Yes, not in this application here that I showed, but it's possible. For example, one of the things that I propose in the end of the code is to use, for example, seismic attributes to enhance our classification. So you can add any seismic attributes that you want. Like the convolutional network is flexible with with respect to the number of inputs. You can input channels. We call these input channels. So you can use seismic amplitude. You can use different offsets. You can use near, mid, far offsets, for example. You can use envelope, energy, whatever seismic attribute that you want. Is very simple. You just add it to the input. So in this case, what I showed is only seismic amplitude, but in the you can use and whatever you want as input, and it
Wow.
usually improves the results.
It's a big question. Thank you, Fernando. The next question is from Leonardo. In the context of semantic segmentation of the F3 seismic dataset using convolutional neural network and PyTorch, how could a semi-supervised learning approach based on self-training techniques be integrated to enhance classification in regions with sparse or noisy seismic data? Additionally, what impact could the inclusion of attributes derived from wavelet transform as additional features have on this process, and how could their relevance be assessed using metrics such as feature importance in interpretable models? Please.
Okay, so the first part of the question, if I understand correctly, the idea is to use what's becoming popular now, like the self-supervised techniques, is where you train your model for one task that does not require labeling, and then you can apply it, like you can adapt it to a new task, and it will perform better on this new task. So for example, what people do is that they train a neural network to remove noise from the data. So you don't need label. You just get your data, you add noise, and you try the network to remove it again. Or to interpolate sparse data. So you get your data, you remove a few traces, and you train your network to interpolate these traces again. So you have the original data, so you don't need labels. So what people are doing is that they're training the networks to do these tasks, and then they fine-tune the network in these other tests. For example, seismic classification that I showed here. And this is a very valid approach. So this usually leads to better results if you do that, especially because you have much more unlabeled data than you have labeled data. So this can for sure improve the results. That can make it this, let's say, the upstream task that's face classification. It can be trained faster as well. So it's a very good approach now that we are seeing. And as for the second question, I think it's related to explainable AI, things like this. It's, for example, in the previous question, if I put a bunch of seismic attributes and I improve my results, I don't necessarily know which attributes were the ones that influenced, like that gave this improvement. So there are several techniques to like for feature importance, as was mentioned in the question, to know which features are more important to get what you want. So it's also a very important like field that is becoming, especially like to have explainable AI. You don't want your AI to be a black box that you have no control on it. So this is go on that direction. But yeah, these are topics that are important. I didn't go on through into them because as you see, there are so many topics that we cannot cover all of them.
Thank you, Fernando. The last one, the next one is the question of Jean-Luc. DGB has developed a workstation to pick automatically all seismic phases. What do they think of these tests?
I'm not familiar exactly with this DGB application. What I saw, for example, in papers, that some people are creating models to predict the RGP, relative geologic time. So this would be equivalent to pick all possible horizons in a data set. I don't know if it's related to that. I'm not familiar with the DGB application. Yeah, but if basically if you have the input data and the target data, you can train a model to perform this task. I'm not familiar with this specific implementation.
Perfect. Thank you, Fernando. The next one, question of Abdel. I have been using Python for machine learning application in seismic domain for years. The first problem we always face is the large volume of seismic data and limitation of computation. Even though using third parties like Google Colab and Google Cloud, any guidance on how to overcome this challenge?
Yeah, so I mentioned in my presentation, for example, one of the limitations that I had in Kaggle was the size of the GPU memory, that we cannot fit all the data at once. So we divided the data into smaller patches. So in this case, that's a more general problem that you have, is that your data does not fit in memory in general. What you need to do is do like partial I/O, partial read your data when you need it, like be more efficient, not try to keep your data in memory all at once. And for that, like there are some Python libraries, like depending on the format of your data, the SegWIO format, that's the more common format for seismic data. I don't think it has really good support for this, but if you convert your data to other formats, for example, based on NetCDF4 or HDF5, that are Python libraries that they do a more efficient, like partial reading, partial I/O of the data. So probably you need to convert your data to these more efficient formats and use one of those libraries to be able to manage the memory better. That's but like each case is a different case. It needs to be maybe something
Perfect.
specific for your case.
Yeah, thank you. Perfect. And maybe data partitioning should be sometimes geographically be considered to be coherent in the geostatistical application that we usually, I have the experience on it, usually try to have this partitioning on large data sets in a way not to distort the spatial structure of the data, because in different domains we have different objectives. In the machine learning, I have less experience about it, so you know better than me. But in some applications, we try to consider some volumes, which is more interesting in order to keep the structures. I think that there's another question. Have you tested? It's a question of Jean-Luc. Another question. Have you tested to improve seismic resolution in Total company? They have performed some interesting results which may increase the quality of your detailed facies classification.
Yeah, I have read some papers on this, like super resolution or like high resolution, like of seismic data. Yeah, it's an interesting application, and it's also maybe can be one of those applications that was mentioned in the previous question that you can do in a self-supervised manner without the need to have the labels. So you can just get your high frequency, high bandwidth data set, for example, and you can like decimate it, or you can reduce the resolution with like a high cut filter or whatever, and then try to train a model to do the reverse step. So this is also a possible self-supervised application. It's very useful as well. In this data set, for example, that we used here, that was provided by DGB, I think that they did the deep steered filtering. So it also, like, let's say in some sense, it increases the resolution in some sense, like it's a filter, deep steered filter. And so, yeah, it can improve. If you have possibility to do other types of preprocessing on top of those that I mentioned, like preprocessing the sense of preconditioning, let's say, of your data, it usually helps. That a lot of works in that regard.
Thank you, Fernando. I think we are reaching to the end of the session, but before ending, at least I want to ask one question from Fernando myself. I cannot prevent myself from asking questions. I waited for the others to see whether they have the other participants have any questions or not. Personally, I'm interested in seismic to well tie, and I'm curious to know whether you have any applications of artificial intelligence or AI or ML in seismic to well tie, for example, for correcting the velocity model, the initial velocity model, or for example, to better model the top horizons or something related to the well logs, please.
Yeah. Okay. The techniques I'm familiar with are like using what's called, I think, dynamic time warping. That's basically you have two time series and you try to match them, stretch and squeeze to match them somehow. That would be equivalent to seismic time. And I think, like, in general, you would need to look into applications that are time series applications, because in this case, the data is more of a time series than it's an image. So depending on what you want to do, if you want to work with seismic phases, you look for image classification or computer vision techniques. In this case, I think you should look into like time series related techniques. In the previous years, we had recurrent neural networks like the LSTMs and so on. I think now everything is moving to transformers. I'm not up to date in this field, so I cannot give you like a good answer, but the works that I saw, like dynamic time warping, that's, I think, is not necessarily machine learning, but it's related to that.
Okay, thank you very much, Fernando, for all these answers and also for the nice presentations you had. If you don't have any final thing to add, I wanted to recall the next events that we have. The next one will be in a hybrid event that you can participate in person at Schellenberger-Clamart or online. It's about distributed acoustic sensors, DAS, from design to data recording and processing. The speaker will be Joël Calves from Schellenberger and Destin Nzegui from Phoebus Optique. That's all from my part, and thank you again, Fernando, and also thank you for all the participants for your questions and for being present for this in this evening. Personally, I enjoyed, and I hope to see you again in another webinar or in another event. Have a very nice evening and have a nice day for Fernando.
Thank you for having me. Thank you for coming, everybody.
See you. See you later.
See you.